Hello, Paolo, to the Nikos podcast. Thanks very much for coming on today at short notice. How
Sure.
are you doing today?
Doing great. Yeah. Thanks for having me. Well, let's chat about some random stuff.
So let's pretend I'm a businessman and I've been spending millions a year on the cloud
hmm
using like central servers for all my data, things like that.
Yeah.
And you come along with this new technology that can basically bypass all the cloud. How can I trust this technology? How can it help me? And how can I be sure that that will be working, it'll be secure?
Yeah. That's a good question. It's a question a lot of people are asking right now. There's enormous pressure on the cloud. There's more and more things that we're doing at the edge. Like these self-driving cars that are producing gigabytes of data per second. These cameras that are doing the same. These devices, all these sensors, all these things that exist out at the edge, they're all putting this enormous pressure on this client server architecture, right? Where client server, right, where you have many, many, many clients to very few servers, and with cloud services, yeah, you're right. There's a lot of cost and complexity associated with that, and a lot of people are looking at what are some of the alternatives? What are some of the other ways we could attack this problem? I don't think it's a binary decision that you need to make. I don't think you need to say, oh, well, the cloud didn't deliver us on the most optimal cost, so we're going to throw it away. I think the the solution we're kind of proposing to people is saying like, hey, the cloud is great, but for there's a lot of pressure on it, and something like Socket helps reduce the footprint on the cloud that your users make, right? By offering you peer to peer to offload some of that work.
Right. So I'm on your website right now and socketsupply.co. So this technology, in a sense, it works peer to peer so that companies and clients, their websites and their customers, they're basically not going through some central place, but they're going, in a sense, peer to peer. For me, this seems like the difference between having like a telephone where you're paying a provider or like using a mobile network versus having like a radio and just like
Uh,
not just phoning something, just pinging someone's frequency on the radio. It just seems so freeing and so geeky, and potentially you could do so much more with that because you could sort of just ping people in range, and you could have a sort of reply back and people in range, or you have some sort of filters. I'm just geeking out about the whole thing, to be honest.
yeah. Well, so I should clarify that there's definitely no range aspect or property to the solution, right? So the peer-to-peer protocol allows an unlimited number of users anywhere in the world to communicate in real time or asynchronously or both. And it's the reason why this is a really big compliment to the cloud is because people are pretty well understand how something like a WebSocket works. For example, like a WebSocket has been around for a long time. People know Socket IO, and they know that that there's a performance benefit in having two peers talk to each other. So gamers are really familiar with this, right? They want to be able to set up a socket where two players can communicate packets directly back and forth between each other because there's just absolutely no sense in bottlenecking that through a single server or service, right? And Socket, it gives you this ability to do that same thing, but without having to set up any kind of servers or use any kind of cloud services. And so, that can drastically reduce the amount of time that it takes to put together a proof of concept or to try to, prove to yourself, hey, can I build a thing that is an interesting idea and would anyone care? That it really expedites this whole rapid prototyping idea.
So that I've tried to use like React Native to build apps, and I've only ever had horrible bad experiences with React Native. I just
Well,
it just
yeah.
never works.
Yeah. Well, to be fair, okay, so we compare ourselves a lot to React Native. We compare ourselves a lot to Electron. and to other kind of newer things that have sort of popped up and tried to address a lot of the problems. You know, React Native was an interesting idea. It definitely helped to validate that people want to use technologies, web technologies, to build software. And so that, I think, we can thank React Native for. It helped to validate this space. And I think Electron did something very similar. It helped to validate that people wanted to use web technology to build software. And you can kind of, stars are a really bad metric because they can be gamed, GitHub stars, I mean. And it's very easy to game them. And so it's very difficult for people to tell, what's really popular and what's not. But, if it means anything to anybody, Electron has 100,000 stars. React Native has 100,000 stars. Even Flutter and I think even Tori has quite a few, right? But these things, the reason why we created this was things like React Native, they fall short in a lot of really fundamentally important ways, right? Like it's a great value proposition to say, hey, you can use something that's kind of like React to create native software. The downside is that React Native doesn't have browser APIs, and so it's not compatible with the rest of the entire web's ecosystem of software. This is just like a huge productivity disadvantage. So while they prove that it's a valuable kind of idea in general, it's a fundamental problem the way that it's executed. And I think the same is true with Electron, right? Electron is in some ways horrible, but in some ways, like it very much paved the way for anything that exists today, right? It proved that people wanted to use web technologies to build software. And, it went through the trial and error that it took to, find the things that did work. And some of those things it does really well. Unfortunately, it produces these massive binaries. It uses a lot of memory. It ships an entire version of Node with it, so the download is really big. But it also ships an entire version of Chrome with it, so it has an enormous binary. Flutter, again, here's a thing that uses a language called Dart, which is an incredibly small market share compared to the number of web developers in the world, which is basically ubiquitous. So yeah, I mean, React Native, definitely, very slow, lots of problems. But, we can say on the upside, it helped really projects like us to, decide that we wanted to do this.
So yeah, I'm using some kind of, say if I'm using Facebook or something like that, and my friends in America, and I want to send them some information, basically, according to my understanding, is what happens is over this web protocol, some IP addresses that I know on my app, the messenger on my app knows the IP address of some Facebook server somewhere. It sends a message and the packet gets delivered there, then gets delivered to the other user in America, and then back and forth. What I don't understand with your technology is that it doesn't seem to be like, well, how does, I just don't understand how a packet from my computer gets to someone else's computer if there's no like determined way to route it, and or we have to depend on like all these little clusters that are set up somehow, and like what's the time to live? How does that actually work?
Yeah, it's a completely different way of thinking about things, and fortunately, it doesn't mean that you need to abandon the way that you already think about things. You just kind of need to add a little bit more perspective, right? So you can, with Socket, I mean, you can still use all your REST APIs. You can do all the stuff that you still do, but you can also add a new capability, right? Which is this thing where people can talk directly to each other, right? And so the question is, how does that happen? How does it even work? It's magic. Okay, so let's dive into that a little bit. Like, let's talk about it. So first of all, like there is no magic. Like the way that a peer-to-peer network starts off is that there are some well-known nodes, right? Now, it all kind of depends on the maturity of the network. Like our network at this point has gotten pretty mature. So, there's tens of thousands of nodes in it that are well-known nodes. So if somebody, gets one of those IP addresses, or if they want to create their own, they're totally welcome to do it. And there's a well-known entrance into the network. So once you have an entry point node, then you tell it, hey, I'm here and I'm interested in a particular thing, which we call a cluster, right? A cluster helps in organizing people, in helping them to discover each other, right? And basically in self-organizing networks where there is no central authority that says, hey, you go here and you go here, you need properties that help to attract and detract people and in nodes in the network, so they know kind of where to go, how to find people. There's some really interesting math that I won't get into called the Strogatz-Watts small network model, where basically the TLDR is 6 degrees of separation, right? It's a small world. Everybody knows somebody, and that's how essentially nodes find each other really quickly. But the way this all starts off is you enter into the network through a node, and it starts introducing you to other people who you want to be introduced to. And usually that happens by when you create an application, you say, well, this app belongs to this cluster. So people who use it, they come into into the network saying, advertising, hey, I belong to this cluster. I'm looking for other people who also belong to this cluster. And so you start to find each other very quickly. Those network paths become very short with the discovery properties of the small world network. And so what ultimately you end up with is people finding each other, but then you still have to determine, how do they actually connect to each other? Because every peer, every computer, whether it's a phone or a laptop, has it's behind a router, and the router has in it a thing called a NAT, a network address translator, and that does the routing that manages the traffic that goes in and out of the router. And those things can have different behaviors, right? Different firewall properties, different port mapping behaviors, and so you have to understand those before two peers can actually connect with each other correctly. And so that's another one of the big problems that comes next, is like trying to figure out, okay, well, how do these things actually decide? What's the proper way for them to negotiate a connection to each other? So this goes on, and there's like a sort of a long explanation to it, and we could even do that if you're interested. But I'll stop there. I'll pass the mic back to you.
Yeah, it sounds like an absolute headache to code, but I'm glad you've solved it.
Yeah, it's the interesting thing is that there is actually a finite problem space, right? It's something that once you understand the properties that matter about those routers, and you understand like the sort of nuances about, well, this is what it takes to discover the properties about them. This is what it takes then to negotiate the connections between them. And once you figured some of that out, it starts to become pretty clear at one point. And I think for us, it's very important to try to start educating people about how this works, because if you're something you said earlier, right, was, well, how do I know that this is reliable? Well, for us, we try pretty hard to science this, right? We want to create reproducible, peer reviewable, evidence-based work that has a real specification. Like, one of the big problems we found in the peer-to-peer space when we looked at this was like, there's like these really cool protocols like WebTorrent, and there's all this cool, interesting internet history, like GNU-net, or Nutella. There's just all these like really interesting internet histories about peer-to-peer, but there isn't a lot of really good material that says, well, this is exactly how it works. There's almost no really good reading material like that. There's a few bits and pieces out there. There's some writers who have written some great stuff about it. The Tailscale guys have written some really good stuff about it. But just like the reading material is really sparse. And another really kind of big challenge is like, most people who are like, hey, I did a peer-to-peer protocol. Well, they did, but they didn't write a specification for it. And, if you don't have a specification, I think Leslie Lamport said this really well. It's like, or maybe I'm paraphrasing, I'm kind of making this up, but basically if you don't have a specification for your distributed system or your, complex, distributed software, then it really kind of amounts to a hobbyist project. It's research. It's not really something anybody can rely on.
So what is the minimum amount of clusters that we need for two peers to be able to communicate with each other?
Okay, so this is a really good question. You actually don't need a minimum of clusters for two peers to connect. So the design of the peer-to-peer protocol is very different from the way that most peer-to-peer protocols are developed, right? So in most cases with peer-to-peer, you've got, five friends and they're like, hey, we're working on a peer-to-peer protocol. And, so they decide to dog food and they're like, well, we're going to create a chat application because that's, that kind of kicks the tires on a lot of the really important aspects of peer-to-peer and all the different little kind of nuances that need to happen. So they build a chat app, right? And everyone's like, okay, well, we're all online and we're chatting and it's fun. And then somebody goes offline and then another person goes offline. Suddenly there's only one guy left online and he's trying to send messages, but there's nowhere for the messages to go. So they can stay on his computer, but then when he goes offline and his friends come back online, now they don't get them, right? So there's a temporal property to this that matters a lot, right? And usually the solution that most peer-to-peer people, including like the Tailscale folks and most other people, what they do is they spin up a server. They say, okay, well, there's either two kinds of NATs that simply cannot connect to each other, symmetrical NATs, or there's the temporal aspect of people just not being online at the same time. And what they do is they say, well, we'll just use a server. So the way, and this is the right diagram actually for this. So what happens is, and you can see here in application A, what happens is, let's just say that, that these three white circles, these are peers that, you want to message them, but you can't, because maybe they're both offline or all three of them are offline. So this blue guy, the guy with the blue lines here, he's like, okay, well, no problem. Like I can't send the messages. So what I'll do is I'll send messages to other people in the network, other people that are online. And these might be people in application B or C. They don't even know the people in application A at all. And that's okay, because the packets that this guy is sending out into the network are completely encrypted. They're encrypted and they're causally ordered. And so what that means is that, these people in applications C and B can receive those packets and they can bounce around and be, fanned out and have a TTL. So they won't burden any particular peer for too long. But eventually what happens is these guys in application A come back online and they're like, oh, well, I'm interested in this particular data. And so these other peers here, when they join the network, a message goes out and these guys say, well, I'm not in your application, so I'm not going to give you a super high priority of replication, but I do see here that there's a packet that you're interested in, so I'm going to give it to you. And so this passive acquisition of packets and this fanning out of packets into the network, it's called network buffering. And so this is a kind of a well-known research space in the delay-tolerant networks kind of area. And we certainly didn't invent this idea, but this is what DTNs, what delay-tolerant networks are really all about, is every peer in the network being able to utilize every other peer in the network to some degree, And knowing, hey, I may not be able to talk to another peer that I want to talk to for potentially a very long amount of time, right? And then so there should be some way without having to use server infrastructure to be able to have those packets continue to live in the network without creating or without incurring like a really big cost on any particular peer in the network. So we don't need servers because we use other peers in the network to float or to sort of buffer the packets when they don't have a place that they need to go. So of course that buffering only lasts for a certain amount of time, right? It's not free storage, right? And there's a kind of limit to how much every peer in the network would be willing to store, because otherwise, like, if I send out a video that's a gigabyte, I don't expect that gets buffered in the network, and all these other peers who don't even know me would have to host that data. That's kind of nonsense, right? But what you would expect is that if I have some state data, right, that's like a couple packets of data, it is really important. Or maybe it's like a couple hundred packets of data. They're only 1024 bytes each, right? So if I have some interesting state data about my application, and let's put it into context, right? Like Alice is trying to play Alice is, so let's say, just doing a chat app with Bob, and Bob is on I don't know, is in the backseat of an Uber car, and they're going through a tunnel, right? So his internet connection breaks for a couple minutes, right? While he's going through that tunnel, right? Well, there's no way for Alice to deliver packets to Bob, right? And so, but there's a pretty reasonable window. It's just a few minutes. Okay, well, those packets can go out to other peers in the network, and then Bob can collect them when he gets connectivity again. And this is like a pretty different approach than most of the way that most peer-to-peer networks are actually working. Most of them are, like I said, providing some kind of server node infrastructure that handles parking, while there's nobody to parking those packets while there's no one to deliver them to online.
So what happens if your socket supply startup becomes huge and a whole bunch of companies start using it, but there's only, like you said, you only have like 1,000 or so well-known nodes? Won't they get like overloaded?
Yeah, so those nodes actually do almost nothing. They do this part of the workflow called reflection, which is just saying, oh, okay, hey, you're here, great. These are some other people. So it's maybe a handful of packets, and there's almost no disk. So there's no CPU really at all. So we've never, even in the current state with tens of thousands of people using the network regularly, we don't have we don't have an AWS bill. There's also a huge percentage of that which we don't really know who's actually running these nodes. So there's people out there who like, for example, we have a Discord bridge. So we have a peer-to-peer chat app that we use. We dog food our product. We use it every day, and the chat application. We decided, well, not everybody in our community is going to want to download another chat application. They might love Discord or whatever. Okay, so we created a bridge. So what that means is we have an EC2 instance that has Discord API running on it, and people can chat back and forth between our peer-to-peer network and our Discord instance. And this is kind of nice because this means we can still have an interaction with our audience over there, but we can continue to use our product the way we want. This is a static node that lives on the network, and we've never had a bill from it, but let's say that it grew. I think that if you compare what our bill is with, which is nothing, with somebody who's got I don't know, 10,000 users, or let's do a little bit of math. Let's say that you have 100,000 users, and you in Discord, and you have each of them sending 10 messages per every 10 minutes, right? So like y- 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 each of these packets that contain the messages is 1024 bytes, right? And then the total number of packets that they can create and send to the network is still less than the amount of data that you would incur over visiting twitter.com without logging in.
Eking out, man.
I mean, like a web page is really expensive. There's so much data that happens. Like there's so much network and so much data that's cost that's incurred by visiting a website. Like even like discord.com or, Slack or any of these things, like you visit these websites and then these like XHR requests, these fetch requests start happening in the background and they start talking to third-party ad services. And then there's like pixel tracking and there's mouse behavioral analysis and there's all this data streaming out, right? There's all this like adware and there's all this sort of stuff that's happening. And I know that stuff's not necessary. Like if you really wanted to compare it like apples to apples, it's like, can you build a web app that's, free of all that junk, free of all those extra, things that because it's unfair to compare, twitter.com. It's basically spyware, right? It's just a massive ad network. Okay. Let's compare, something else. I don't know. Like Mastodon is actually like a good example because it's like, it does a lot less of that garbage, ad net stuff in the background. So like, even with that, you end up with quite a bit of client server requests and having all of this infrastructure that's required to and expertise that's required to run that. And so all of this kind of amounts to a far more significant amount of data through the pipe than it is to introduce peers together. And once the peers are connected, then there's no cost for anybody.
Cool. Well, I have to run because I have a hard schedule today. But Paolo, thanks so much for coming on. I will be streaming about this stuff probably on Twitch and building stuff with it. But I know you're really busy traveling around talking to people and that. But anything you want to share with us before we finish this one?
Yeah. So, just go ahead and go to our GitHub, socket supply /socket and, start the project and try it out and, give us feedback however you want. Of course, through GitHub is ideal, through Discord, or if you want to join our peer-to-peer chat, that's absolutely, we can give you access to that too. We're doing a small pilot program. We just created it. So, we're just trying it out. But I would invite people to just come and try things and chat with us. We're happy to meet new people.
Okay, cool. Thanks, Paul. I'm sorry it's such a hard stop today, but
no
I'll see you in Discord and we'll be building stuff and
all right, cool, man.
Playing with our personal radio internet stuff.
Yeah, totally. All right.
See you later.
Cheers.